to thank you, all the persons that are working hard to succeed this conference. I also would like to thank the PhD students, the doctors, and the researchers for their presentations. Now it's my turn to present you our work, where we worked on the optimization of fuzzy logic model for our proactive maintenance under the supervision of my professors, Professor Assia Kamal-idrissi from the International Center of Artificial Intelligence of Morocco at Mohammed VI Polytechnic University in Rabat, Morocco. And also my professor Amal Fallah Seghrouchni, the head of the center and professor at Sorbonne University, Paris in France. I would like to mention that this work is a joint work between the EI movement, or the Center of Artificial Intelligence, and the OCP maintenance solution. So here is the agenda of the presentation. I will start first by an introduction. Next, I will present the research problem or the research statement. Then I will represent some of the related works. I will also move to the objectives, our objectives. Then I will show follow the methodology and the experiments and the results. Then I will conclude my work, my presentation, and give our perspectives. First, I want to take you a few years back to present the revolution of industries during the years. The first industrial revolution appeared in 1784, where we used water and steam power to mechanize production. At the year 1817, within the electricity operation, we used it to create assembly lines and start mass production. Next, in 1969, industries started to use robots and computers to automate productions. Now, the ongoing fourth industrial revolution uses information technologies to collect data from physical world and the digital world. Now, within the fifth industrial revolution, it is expected to bring the human back to the center of operation through a human cyber physical system for value creation and human robots collaboration and integration. So as industries evolve, so maintenance strategies do. We have started first with corrective maintenance, where we used to let a machine continue functioning until it breaks, then we repair it. Passing to time and condition-based maintenance, where we repair or replace an equipment of a machine after a certain time of functioning, or when the degradation levels of a machine reach some predefined levels based on standards, which is the concept of preventive maintenance. Then we try to improve this strategy by processing the signal data collected from the machines and using machine learning algorithms, we've been able to predict when a machine will fail in the context of our predictive maintenance. Now we are aiming to have more advanced strategy because in a predictive maintenance strategy, its mission ends in telling us when a machine will break down. In the absence of a failure diagnosis, the cause, the nature, and the absence also of a tool that can provide optimized actions, then that requires a full process from diagnosing to maintenance decision-making. This enters in the concept of prognostics and health management and root cause analysis, which require expertise and knowledge, and a call for a collaboration between human and machine. So what is what is the prognostic and health management? Prognostic and health management provides a decision support to reduce maintenance costs and time by applying efficient and cost-effective diagnostic and prognostic activities. It is consists of 5 blocks: data acquisition, anomaly detection, failure diagnosis and failure prognosis, and maintenance decision support. However, maintenance and the choice of maintenance strategy is critical. These are some statistics that shows the importance of machine actions, maintenance actions. The cost of maintenance can change from an industry to another, depending on the activities. It can go from 15% of goods produced in food-related industries to 16% in heavy industries. So the performance of an industry is related directly and indirectly to maintenance activities. That's why industries are aiming to reduce the non-quality and breakdowns costs, and provide the most adapted and reliable and profitable industrial tools for better productivity, and also ensure the availability of all companies' equipment at an optimum cost. So passing to the research problem, as I said, this is a joint work between the Artificial Intelligence Center and OCP Maintenance Solution. We are trying to improve one of them tools that they have developed. This tool is aimed to predict machines' remaining useful life using machine learning algorithms, and it also gives alerts to agents of maintenance for the upcoming failures. However, this tool is covering only 4 blocks of prognostic and health management. Moreover, the limits of this approach are represented in the fact that the definition of the cause and the nature of a failure is done based on classical method, which is failure mode effects and criticality analysis, FMECA, on the results, which is done manually. So it's only this tool is only predict the remaining useful life of an equipment, not its future state detail. And the use of the FMECA approach is not automated. It takes a lot of time and requires experts to get it done manually. It does not diagnose the current state of an equipment, since the FMECA method is it takes time. So we are diagnosing, actually we are diagnosing the past state of the machine, not the actual machine state. Also, there is an absence of a decision-making tool that helps maintenance agents to make precise decisions. So for those who doesn't know what is the FMECA refers to failure, as I said previously. FMECA refers to failure mode effects and criticality analysis. It is a procedure that is performed after a failure mode effects analysis to classify each potential failure effects according to its severity and probability of occurrence. So passing to the related work and what exists in the state of the art, the FMECA approach is widely applied for different purposes and considered as an essential part of maintenance management strategies. An example of application is given by Xiaoqing, where he applied the FMECA approach to analyze the reliability of a metro door system. And about fuzzy logic, and I will go through it later, this approach has been applied to analyze FMECA results, determine the priority of maintenance on the equipment of a cooling system. There are, of course, so many other applications of the FMECA, but I will present only these ones. So, however, the limits of these approaches are multiple. Starting with FMECA, and besides the time it takes to obtain the results, the limits lays in the subjectivity of expert judgment, and also in the inability to deal with uncertain failure data. Also, the absence of analytical basis in the risk priority number calculation formula, and many duplicates in the risk priority number results. Secondly, the fuzzy logic tool The limits are well, there is no method to define or justify the input memberships, and also the rules of the fuzzy logic approach are manually generated. There is also no algorithm that guarantee the consistency and the non-redundancy of rules, which greatly impacts the time complexity. These limits have led us to define our objectives that can be represented in research objectives and industrial objectives. So the research objectives are, first, we are aiming to automatize the FMECA approach to save time. The second objective is concerning fuzzy logic tool and aiming to overcome the issue of what membership function type is suitable to use. And finally, optimize and generate fuzzy logic rules. So while concerning industrial objectives, we are aiming to develop an AI-based tool that overcome all that cover all the 5 blocks of prognostics and health management, which proactively supervise, identify, and predict failures, and also recommends optimal decision for maintenance agents to take actions. So to achieve this, we put the following methodology. First, there are collected data from different sensors that can be exploited and used to determine recommendations for the deciders. First, as you can see here, the collected data can be either vibration, oil analysis, temperature, or acoustic data, or even images and videos. And this data need to be corrected and pre-processed and saved into the database. And here is the artificial intelligence part comes. This data need to be analyzed based on artificial intelligence technique for machine diagnosis and prognostic results. And prognostics, and also the integration of the experts' knowledge is useful for interpreting the diagnosis and prognostic results, which eventually taken into account in the phase of recommendation generating. So concerning diagnosis phase, which first start with collecting data and use statistics and AI techniques to analyze it. Secondly, using fuzzy logic techniques to integrate digital data and expertise knowledge to properly diagnose a system and eliminate the uncertainty and the vagueness of trying to understand these data. Then, based on the outputs, generate recommendations for maintenance agents to take actions. And for sure, the communication between the system and human is done in real time through human-machine interfaces. In our work, in this presentation and in our paper, we are only focusing on the diagnosis phase using fuzzy logic approach or technique. So what is fuzzy logic? Fuzzy logic is a process of giving conclusion and decisions from an uncertainty problem. Before fuzzy logic, there were the Boolean logic that gives only 2 values. One is 0 and the other is 1. That is low or high. No other values can be found in this logic. While fuzzy logic gives the extended view such as low, very low, high, very high, and very high, and so on. So the most well-known system is the Mamdani rules-based one. It used the following rules. So first of all, fuzzify all input values into fuzzy membership functions. Secondly, execute all applicable rules in the rule-based to compute the fuzzy output functions. Defuzzify the fuzzy output function to get crisp output value. So why we choose fuzzy logic. First of all, the characterization of the degradation phenomenon of any machine involves some degree of uncertainty in vagueness, and also the desire of the decision makers to express criteria values in linguistic term introduce vagueness into the metric criteria analysis. So as I said before, there were only the Boolean logic, which the answer can be either yes or no. And now with fuzzy logic, the answer is maybe. So the value ranges anywhere from 0 to 1, from no to yes, from low to high, etc. About the experiments that we've done. So in this study, we've tried to answer, first of all, in this study, we've tried to answer the following question that are referred to research objectives mentioned before. So the first question, can the inclusions and intersections impacts the output of fuzzy logic controllers? The second question says, how can we intelligently generate optimized fuzzy logic rules? And the last one, which one of the fuzzy logic membership functions is the best for our case? So here is our representation of the data used. It is composed of a list of digital data collected from 4 sensors. Each sensor has a list of lists of acceleration time waveform, velocity spectrum, and acceleration spectrum. This data also composed of knowledge data that are carried out by OCP maintenance solution experts using the FMECA approach to identify the machine state and its cause. As you can see here, they have stated 7 state machine states from a normal state and 6 type of failures. So our proposed model, we call it integrated truth table and fuzzy logic model. So we gave him input values, and based on the fuzzy logic, he gave us he gave us in generally the machine state. So in the preparation phase, we have calculated, first of all, the root main cause of each list, then defined the minimum and the maximum value of each list for both velocity and acceleration spectrum to have eventually a range corresponded to each machine state. So we have just defined the minimum and the value and the maximum of each interval, and this allows us to save the information of the data. And here is our presentation of the obtained range of different machine states. To better understand this, as you can see here, these are for example, this is the interval of normal state for the acceleration spectrum, and this is the interval of normal state for the velocity spectrum. So to give an example, for example, if we take 2 values here for the acceleration spectrum, if we take this value over here, and for the velocity spectrum, if we take this value, they belongs to these two intervals or machine states. So for this one, we have normal state and Beron lubrification fault, while in the velocity spectrum, the value belongs only to normal state, which means that the machine state now it's in its normal state. While if we took this example over here, so here we have this value belongs to bearing lubrification and gear fault and also mechanical looseness, but in the for the acceleration spectrum, the value belongs only to the gear fault interval. This means that the machine suffers from a gear fault. So this one is much complex example. So this value can be belong to all the 6 intervals and also here. So we cannot know either it is a gear fault or a bearing lubrication fault or a mechanical looseness fault. And this is, and here the fuzzy logic can help us to solve this problem. So with the help of the experts and based on the knowledge, this is a table of truth which represents which state is corresponding to the 2 input variables, velocity spectrum and acceleration spectrum, using the AND operation. We only selected the existed cases. So when the velocity spectrum value is inside the range or the interval EV1 and the acceleration spectrum is inside the interval EG1, so automatically the machine is in its normal state. While, for example, over here, if the value of the velocity spectrum is in the EV in the interval 5, and the acceleration spectrum value is belongs to the interval EG5, so the machine state will be in a mechanical looseness state. This is as we saw in the previous slides, there are some intervals that include other intervals that will cause vagueness, so we cannot define which state is the actual state of the machine. That's why we detected these inclusions and save only intervals that includes another intervals. So the last table is the new optimized table, truth table that we've got. As you can see, if, for example, over here, if the velocity spectrum value belongs to the interval EDV4, and the acceleration spectrum belongs to the value belongs to the interval EG1. So the machine state can be in a structural fault or in a misalignment fault. And also here for the last example, we have 2 states over here. So this can be used to generate fuzzy logic rules. As you can see here, this is a table of rules generated from the previous optimized table of truth. These rules, we will use them in the second step in the preparation of our fuzzy logic model. So if if the first term and the second term, then we have the output. Passing to the preparation of the fuzzy logic model, the first one, we define the machine state intervals, and as you can see here we have all the seven machine states from normal to gear fault, one normal state and six gear faults and 6 failure mode. As I previously mentioned, in our research objectives, we are trying to figure out which membership function is suitable for our case and how can we justify our choice. Noting that there are 3 membership functions that can be used in a fuzzy logic model. There is Gaussian membership function, triangular membership function, and trapezoidal membership function. And so many authors used one of these membership functions without justifying their choice. Now, this is how Gaussian membership function looks like. These are two input variables. Here is the acceleration spectrum input variable, and here is the velocity spectrum input variable. So, and this one, well, after we run the fuzzy logic model, this is one result of the experiment we've run. So this table conclude we have run 14 experiments, and this table shows the obtained results of Gaussian membership. As you can see, it only gave 4 correct cases. The other cases either gave false results or it didn't give any results at all and showed an error. This is because of when we defined the input variables using Gaussian membership, the intervals were not connected, as you can see over here. So they are not fully connected. So the gap over here and the distance over here caused these problems over here. This means that this model isn't the best choice for our case. Passing to the triangular membership function, there is the input variable. There are the input variables. The same here is the acceleration spectrum, and over here the velocity spectrum. And this is a result of one experiment that we have run. It gives, well, the results here are showing like in an accuracy of 16%. And the same here, we have, the table that conclude the results of triangular membership. It gave 7 accurate results with an accuracy that goes from 15 to 95%. Passing to the trapezoidal membership function. As you can see here, the inputs definitions also here, this is corresponding to the acceleration spectrum, and this one is for the velocity spectrum. As you can see, it saves the connectivity between intervals and cover much more range for each interval. And in here on the right, one of the experiment results with an accuracy of about 98%. This table conclude the results and summarize the 14 tests we've run. It gave 9 accurate results with an accuracy between 15 to 100%. This is a summary of the summary of the obtained results for both membership functions, for the 3 membership functions. For example, here for the Gaussian membership function, we only had, I guess here, actually 4 of 14 results, correct results of an accuracy of 15%. And the triangular is 7 of 14 with an accuracy of 75.85%, and the trapezoidal 9 accurate results, correct results with an accuracy up to 18%. So this can answer our third question. The trapezoidal membership function is the best for our case. Comparing this to the existing approach or tool used by OCP maintenance solution, their tool can only give 2 sorts of outputs: a normal state when everything is correctly running, and alarm when there is some malfunctional state. While our tool offers constantly and immediately the machine state with an accuracy up to 18% in average. So to conclude, we have succeeded to automate the FMECA approach and optimize the fuzzy logic rule. And also we have concluded that trapezoidal membership function gave better results. In short term, we are aiming to integrate the multi-criteria aspect and use knowledge graph to interpret and to interpret the results, and also we will compare it to the results obtained by fuzzy logic. And in midterm, medium terms, we are working actually in parallel with are working on the prognostics and decision-making tool. So thank you for your attention.